Since you're here, I'm guessing you've probably seen this formula before. However, as it is with just all the numbers, it doesn't really say a whole lot. But underneath the hood, there is some truly foundational math. Because on the one hand, you have calculus, which is used, well, all over the place, simulating, optimizing, you name it. And on the other hand, we have linear algebra, which is also used for all of those things, but in different ways. The point is, both of these very broad topics of mathematics are used all over the place. In fact, your GPU is certainly using a lot of techniques from linear algebra just to let you watch this video, and I wouldn't be surprised if there was some calculus thrown in as well. The point is, both of these are used all the time in pretty much any scientific endeavor that you can think of. And this formula, and the more general one beneath it, are at the center of the two. And understanding just how you get to this place is enough to lay the foundations for some of the most important applicable mathematics there is. So let's start with I. I is defined as a number that squares to -1. So over here, we have that 1 times I times I is -1, -1 times I is -1, and negative I times I is 1, and then it just keeps on going in a loop. Now, what this also means is that 1, which represents the right direction, when you multiply anything in that direction by I, it turns into an up. You multiply anything up by I, it turns into a left. And you multiply left by I, down, and you multiply down by I, and you get back to right. So any number that's in one of those 4 directions, when you multiply by I, it will rotate 90 degrees counterclockwise. And since any number can be broken into a horizontal and a vertical part, like a plus bi, and multiplying by I rotates both of those parts individually, the whole thing rotates 90 degrees counterclockwise. And what this means is that any number on the plane, when you multiply by I, gets rotated 90 degrees counterclockwise. So if you have a number that's right plus up, it will turn into an up plus left, like right here. Now, more generally, what happens if we multiply any number a plus bi times some other number, and let's call this one w, when we distribute, the a turns into an aw and the b turns into a biw. And iw is perpendicular to w. So we take right and up, and we send them to w and iw, perpendicular, 2 perpendicular directions to 2 other perpendicular directions. So that guarantees a rotation by that angle theta that separates w from the horizontal. Now, additionally, if w has an absolute value, basically a length of something other than 1, it will change the length of all of the other directions as well. However, for this video, what's really important is what happens when the length is exactly 1, which means nothing gets stretched, only rotated. Now, before I go on to the next bit, I'd like to note that the whole idea of taking standard directions and mapping them to specified directions and having that tell us where everything in the entire plane goes, or an entire higher dimensional space, is at the very core of linear algebra. So this one concept is enough to get you very far when dealing with vectors and what are called linear transformations of vectors, which are incidentally represented by matrices. In fact, let's take a closer look at this. So over here, we have essentially what a vector looks like. It's essentially a coordinate pair, A, B, A in the x direction and B in the y. And note that we call the x direction vector of length 1, 1, comma 0. And we call the unit vector in the y direction 0, 1. And we represent them as columns. So let's look at this matrix, which has 2 columns, 1, 0, and 0, 1. And let's see what happens when we multiply a vector, AB, times this matrix. Well, the way matrix multiplication works is we end up with A of the first column and B of the second. And, well, here's the thing. The first column is just the x direction, and the second column is the y direction. So when we add it all up, we just get back AB. So this matrix we call the identity matrix because It just sends the x and y to x and y, just like multiplying by 1. All right, let's look at one more matrix. This one has columns 0, 1, and -1, 0, which means it sends the x direction in blue to up. It sends right to up. And it sends the y direction up to left. Right to up, up to left. This might sound familiar, but when we multiply through by this, we get a of the ups and b of the lefts. So that's b left and a up. But we've definitely seen this before, because when we multiply a plus bi times I, we end up with minus b plus ai. The right turns to up and the up turns to left. Everything gets rotated, which means that this matrix thing and this I thing are exactly the same thing, because they both send the same directions to the same directions. All right, now let's put this together. So we have the identity matrix. And we have the second matrix, which I'm going to call R because it's a rotation, 90 degrees, just like I. And if we take this number a plus bi, which I'm going to call z again, we can associate this with a of the identity matrix, which is like 1, and b of the rotation matrix, which is like I. And if we add this together, a of the first and b of the second, we get this matrix here, with a's in the diagonals and a b and a minus b in the off diagonal. And one more interesting thing to note here is that the first column of this is AB, which is Z, and the second column is minus BA, which is I times Z. So this matrix carries with it all of the information needed to multiply some number by A plus BI. It carries the Z direction, it carries the IZ direction, and it sends X to the Z direction and Y to the IZ direction, which is exactly what happens whenever you multiply by some complex number. So in a very real sense, matrices like this are the complex numbers a plus bi. And note that in the matrix, there's no I. There's only a's and b's, which means that these so-called imaginary and more generally complex numbers are really, really just real two-dimensional objects. But beyond that, though, what we see about linear algebra and matrices in general is, first off, that they subsume this set of two-dimensional numbers, but also that we can pick anything we want for the columns, which means that these things generalize not only to different kinds of transformations, but to any number of dimensions. And ultimately, that's where the power of linear algebra lies, because there is a lot of stuff that we can allow to happen. But analyzing each of those steps is just a question of sending the usual directions to a different set of directions. And now back to the main video. So here we have a unit circle, which is a circle of radius 1. And we can draw right here a right triangle inside the circle with hypotenuse 1. And since we have a right triangle with hypotenuse 1, the adjacent side must be cosine of that angle, and the opposites must be sine. So the point that's on the circle, that angle away from here, is cosine theta plus I sine theta, which we can denote CIS or cis theta. Also, a nice thing about this particular definition of cosine and sine is that we don't need to be able to draw a right triangle in, up in the first quadrant here. We can go anywhere on the circle and stop, say at angle phi, giving us the point on the circle cis phi. And also, quick note, we have cis phi here, and 90 degrees this way, we have the perpendicular direction, which is I cis phi. That will be important later. So let's put this together with what we know about generally multiplying by a number, that it rotates by a given angle, and if the length is 1, which all of these CISs are, then all it does is rotate. So if you multiply by cis theta, you will rotate everything by angle theta. And if you multiply by cis phi, you will rotate everything by angle phi. So what happens if we multiply these two numbers? Well, then we'd be performing a rotation followed by another rotation. Multiply by one, multiply by the other, which means we're going to end up multiplying by the sum of those two angles. So we have cis theta times cis phi equals cis the sum of theta and phi. Now, there's a chance you've seen something like this before, particularly when working with exponential functions. Take 2 squared times 2 cubed. Well, that's 2 2's and another 3 2's, so we end up multiplying by a total of 5 2's. So the exponents are 2 and 3. We multiply those powers together, and the new exponent is 2 plus 3. And this is a general property of exponential functions. So what we've shown with cis theta times cis phi equals cis of the sum of the two, what we've shown is that it has the exact same property as exponential functions do. And that gives us the equal sign in the original formula. You may be a little bit unconvinced because maybe you're thinking, shouldn't exponential functions do like that, where they get bigger and bigger and bigger in the case of exponential growth, or flip that, smaller and smaller and smaller for decay, but they're not generally supposed to go around and around and around, right? Well, here's an interesting one that doesn't even require any i's. Let's take -1 to the power of n, where n can be 0, 1, 2, 3. For every even power, it's going to be 1. -1 squared is 1. For every odd power, it's going to be -1. -1 cubed is -1. So it's just going to be bouncing up and down between +1 and -1. And I've gone ahead and creatively connected the dots a bit there, just to give you a little hint at how wavy this really is. So it is exponential, and it's definitely cyclic as well, and it definitely doesn't have any i's in it. And also, as a quick little note, it is interesting to notice that this multiplication by -1, which on the real number line is a bounce off from here and end up here, well, in 2D, it's just a 180-degree rotation that gets you pointing opposite to where you started. So it's always, so multiplying by 1 has always been a rotation. It's just you can only see it in 2 dimensions. But let's get back to this exponential function here, specifically 2 to the n, where again, n can be an integer. So it can be 0, 1, 2, 3. It could also be negative. But let's look at the very particular behavior of multiplying by 2 again and again and again. So let's start with 2 to the 0, which is 1. So when n is 0, we have 1 of something. Now when we up n by 1, we are doubling. So we gain 1 of something. And similarly, once we have 2 of something, once we double, we gain 2 of that thing. And once we have 4, we gain 4. In other words, 2 to the n, doubling, means gaining exactly 100% of what you just had every single step. So it's very special that way. And that 100% is going to be really, really important. However, the function we're working with, cis theta, isn't just jumping around the circle, like, for instance, I to the n would. So you go bum, 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 around and around. So I to the n jumps around the circle. But cis theta moves smoothly around the circle as theta increases. So we're not going to be able to get away with just talking about discrete intervals like double, 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 or 1, I, -1, -I. We need to be able to talk about exponential change that happens smoothly, which means we're going to have to talk a little bit about average rates of change versus instantaneous rates of change. Now, an average rate of change is like average speed. So you travel this far over this amount of time, you divide one by the other, you get average speed. And notation-wise, there's those little triangles there. That's a Greek letter delta, which is basically a d for difference. So it's the difference in y over the difference in x. So again, some average rate of change, which also is a slope. Now, on the right side, we have something a little bit different. We have a slope again, but of a tangent line. And this represents instantaneous rate of change, like instantaneous speed, which we normally just call speed. So at a particular moment, you are traveling at a particular speed. And if you were to remain at that same speed for the foreseeable future, you would go off along that line. So going at the same speed would represent going along that same slope. Now, we don't stay at that same exact speed generally, but that's okay. All we need is the notion of speed or rate of change right now. And again, quick little note, that d, it's also d for difference, except there is a limit involved, so we can't be too literal. But again, it's still a slope, and ultimately there's a difference quotient behind it. So the point is we can use the notation and not worry about it too much. So let's get back to exponential functions again. And on top here, I've drawn 2 to the n, so the blue dots, which take us from 0 to 2 to 4, and I've drawn in that blue dashed line, which has a slope of 1 from 1 to 2 and represents 100% growth. But it's an average growth rate, not instantaneous, and we need instantaneous. So I've also connected the dots with a curve, which it represents 2 to the x, where x can be, well, pretty much anything. And you'll note that it dips beneath the blue dashed line, which means that the tangent line, the red, has a slope less than 100%. So the instantaneous growth rate is less than 100%. And I've included roughly the specific number there, but again, less than 100%. And similarly, with 3 to the n, or 3 to the x, the blue dashed line, because we're going from 1 to 3 in a step, that's 200% growth. But if we're looking at the instantaneous growth rate, it's less, because again, it dips below the blue. But this time, it's still more than 100%. So if we want an exponential growth function which has an instantaneous growth rate of exactly 100%, we're going to need something between 2 and 3. And that brings us to the number e. So the blue curve is e to the x. And when x equals 1, y is e, which is roughly 2.7. And in particular, the red dashed line is pointing in the direction of 100% instantaneous growth, i.e. with a slope of 1. And by the way, if you've done compounded interest before, then this might be familiar, because ultimately that's what that whole 1 plus 1 over n to the n deal was. It means that you were aiming for 100% growth, but you started compounding instantaneously. So you immediately leave the 100% line. That's e. So what we have now is an exponential function whose rate of change is exactly 100% of itself. Whereas the instantaneous growth rate of 2 to the x is less than 100% of itself, the instantaneous growth rate for 3 to the x is more than 100% of itself, we have that the growth rate for e to the x is exactly 100% of itself, i.e. it is its own growth rate. And that is what we're going to need. Oh, and by the way, there's another word, derivative. It just means instantaneous rate of change. It's a dumb word. Now we just need a couple more tools to really finish this thing off. And one of those is what happens when it's e to the something other than x, like e to the 1/2 x. Well, e to the x when x equals 1 is e. But for e to the 1/2 x to be e, we need 1/2 x to be 1, which doesn't happen until x is 2. And everything else is also delayed by the same factor of 2, i.e. the entire x direction gets stretched by a factor of 2, which also means that the tangent lines get stretched this way by a factor of 2, which means they are only half as steep. So the rates of change are all half of what they would have been otherwise. Which means in general, if we have e to the kx, where k is just a number, then to get the rate of change, the growth rate, we have to multiply the original function by k. And it's important to note that any exponential function can be represented as e to the kx for some k. And it's also kind of worth noting that the natural log, so ln2, is defined so that e to the ln of a thing is just the thing. So we need, sure, we need one extra tool to do it, but not too important. What's important is that any exponential function can be rewritten as e to the something times x. And the very last tool that we need to bring this all together is just to define our angles carefully. So typically, and especially for this purpose, we tend to use radians. And a radian is defined so that on a circle of radius 1, if you change the angle by 1 radian, you will travel exactly 1 unit along the circle, which means the angle, written there as theta, is equal to the distance you travel around the circle. And a full circle is the circumference of a circle of radius 1, namely 2 pi, which we can also write as tau, as in a turn. So 1 tau is a full turn, which is helpful, and it's also kind of its own thing. And in general, if we have a circle that's different radius, then the ratio stays the same. So the distance around the circle is r times the angle. But for now, we are really interested in the circle of radius 1, where for every unit change in the angle, we travel 1 unit around the circle, 1 to 1. And now we're ready to finish this thing, because we've established that cis theta is somehow exponential. And we know that exponential functions have rates of change that are something times themselves. And once we have that something, we can immediately infer what exponential function we are working with. And with cis theta, that number is a point on the unit circle, a distance of 1 from the center. It has a length of 1, and it's traveling counterclockwise around the circle at a speed of 1. How do we know it's 1? Because radians. For every unit change in angle, we go 1 around the circle. The speed is 1. And more than that, we know that it is traveling in a direction perpendicular to itself. Specifically, the perpendicular direction rotated counterclockwise. So, and we also know that when we multiply a number by I, it rotates that number a quarter turn counterclockwise, and it does not change the length, which means the that the speed of it, the instantaneous rate of change, is exactly I times itself, which means that cis theta is e to the I theta. And that completes the formula. Well, one quick note, we do need to note that cis 0 is 1. It starts out, which is necessary to note because e to the 0 is also 1. If cis 0 were, say, 2, it would have to be 2 e to the I theta. But it's not 2, it's 1, so we are done. Now, there are far too many applications of this formula to go into right now, and by now I'm sure you need a bit of a breather. But let's take a quick look, at least, at some of the dominoes that start to fall immediately, and just how quickly they do so. Starting with the double angle formulas. Up top, replace theta with 2 theta. Bottom, take the whole e to the I theta and square it. Either way, it's equal to e to the I times 2 theta, and a bit of foiling down bottom gives you the double angle identities. Next up, we have the derivatives of cosine theta and sine theta, which we can get by, well, just multiplying the whole thing by I, because it's e to the I theta. So matching the blues, we have that cosine's derivative is minus sine, and matching the orange, sine's derivative is cosine. To the right, I have a half period of both cosine and sine. And for each one, I have marked values in black and rates in red, and there's enough there to compare and confirm. And of course, the special case you get by plugging in pi, and a half turn around the circle gets from 1 to -1, and that's basically where that comes from. Not particularly happy with the moving the -1 to the left for a plus sign, but hey, to each their own, I guess. But the big takeaway is that e to the I times some fraction of tau is a rotation by that fraction of a circle. And that's just a few, because with all of the links to sines and cosines and other cyclic functions, and all of the exponential stuff, and all of the rotation stuff, and all of the other stuff, this formula gets an immense amount of use in, well, you name it, math, sciences, engineering, and anyway, I hope you enjoyed some of this. And at any rate, I think I promised you all a breather, so bye now.